Hi guys, welcome to this set of videos. Again, what we're doing is we're working our way through several sections here where we're talking about proving the congruency of two triangles and ways that we can go about showing triangles are congruent. Now what we did initially was we talked about the Cpctc Theorem, which says corresponding pairs of congruent triangles are congruent. But that required us to do a lot of work. We had to show or prove that all three pairs of corresponding sides and all three pairs of corresponding angles in a triangle were congruent. That meant we had to prove 6 things, which was a lot of work. So then in the last section, what we saw was there was a shortcut. We saw that if we could prove 2 angles and the included side, so angle, side, angle, if we could prove those 3 things, that was enough to prove the triangles were congruent, and essentially we cut our work in half. Turns out there's another shortcut. So let's go ahead and jump right into this by first taking a look at our essential question. Here's what you guys are going to do. What does SAS, Triangle Congruence Theorem, tell us about triangles? Well, at this point, I imagine you could probably figure out what the abbreviation SAS stands for. Of course, it is side, angle, side. Now, in order to answer that essential question, several things that you guys need to know, objectives that you guys are going to need to know as we go through this. I apologize, I got a couple of typos in here, right? Angle, side, angle, that was the last theorem we looked at. Just go ahead, cross that out, put SAS. Cross that out, SAS, cross that out, SAS. Apologize for those typos. I don't mean to, but sometimes, I don't know, I just get going too fast and make mistakes. Anyway, guys, here's what you're going to do, right? Really simple. First, we're going to decide whether triangles are congruent using side, angle, side congruence theorem, so we'll talk about what it means. Then you're going to prove triangles are congruent using the side, angle, side congruence theorem. And then, of course, again, I don't know how many times I've said it at this point, I also teach algebra, and any chance I get to do algebra with you, we're gonna do it. So we're gonna go ahead and find missing side lengths and missing angle measures using side, angle, side congruence theorem. So let's jump right into this by taking a look at what is the side, angle, side congruence theorem. Well, I've got it for you right here. All right. Here's what it says. Again, a couple of important things here I got to point out. If 2 sides and, you ready? Look, included angle. Guys, we saw that the last time. I'm going to spend a little bit of time talking about why, right? In the last section, we talked about why it had to be the included side. Here, I'm going to talk about why it has to be the included angle. We'll show you why. I promise it'll make sense. So if 2 sides and the included angle of one triangle are congruent to 2 sides and the included angle of another triangle, the triangles are congruent. And again, remember why this is important. Cpctc required you to prove 6 things. 3 pairs of corresponding sides, 3 pairs of corresponding angles. This theorem cuts our work in half. Cpctc required you to prove 6 things. This theorem only requires you to prove 3 things. 2 sides and an included angle. Half the work hopefully means half the time, right? Working smarter, not harder. Let me show you how this guy goes. Here's what I got. I want you to think about this for a second. Let's put our thinking caps on here. Use our imaginations. What I've done is I've given you 2 sides of a triangle. 3 inches, 2.5 inches, and 1 angle. 45 degrees. Now, my theorem says the angle must be the included angle. Let's take a look at why it has to be the included angle, meaning the angle between the 2 sides. And here's how we're going to do it. Let me draw you 2 quick little diagrams. This will be real easy and pretty painless. Here we go. All right. One of my sides is 3 inches and it's at a 45-degree angle. Let me go ahead and draw that. Again, probably not to scale. I'm trying. There it is. 45 degrees, 3 inches. Let me draw the exact same thing over here on the other one. Again, I apologize that those are not exactly to scale, but you guys get the idea, right? I've been given two sides and an angle. So I've got two different figures. One of those sides, 3 inches, 45, and 45, right? That's this guy. Now, what I still have is one more side. I have this side right here that's 2.5 inches. How many triangles can I make? Well, you can already see that I can get two, and here's the reason why. That 2.5 inch side could either, this guy right here, could either go right here, 2.5 inches, or hopefully you guys, right, can you picture this? It could go right here, 2.5 inches. Do you see how there's two different triangles? I can get, look, right? Side, side. This angle is not included, right? If it were the included angle, it would be this one right here, right? But it's not. I have side, side, and then an outside angle, right? An angle that's not between my two sides. Same thing here. Side, side, and a non-included angle. When the angle is not between, included means between, when the angle is not between the two sides, I get two different triangles. A non-included angle will produce two different triangles. I could get this one with a side length of 3 and a side length of 2.5 with a 45-degree angle. I could get this one. But I could also get this one with a side length of 3, a side length of 2.5, and a 45-degree angle. That's when the angle is not included between the two sides. But now let's talk about what the theorem says, right? The theorem says it must be an included angle. Here's the reason why. Look at this guy, right? If 45 degrees is the included angle, so right there, there's my 3 inches, right? This is my side that's 3 inches, my 45-degree angle, and then that other side that's 2.5 inches. Well, if I put that side that's 2.5 inches, right, so that my 45-degree angle is between my two sides, how many different triangles can I draw here? Yeah, there's only one way to connect those two sides, and it's with this guy right here. Right? Guys, that's the whole point. If it is not an included angle, if the angle is not included between the two sides, then it's possible there's two different triangles that you could get. But when it is the included angle, when it's the angle that's between the two sides, because there's only one possible triangle that you could get. One unique triangle is produced. IQUE, one unique triangle. So here's what that means. Here's what that means. If you know two of the sides and an included angle, that means that there's only one possibility, right? One unique triangle. There's only one possibility for that other side length, right? What that does is allows me to find two side lengths and an included angle, and I'll know that the other two angles and the third side must also be the same. Because there's only one way to draw a triangle if I know two of the sides and an included angle. This is it. It has to look like this. So if I can show that two triangles have two sides that are congruent and an included angle that's congruent, the triangles must be the same. Because there's only one way to draw a triangle when you know two of the sides and an included angle. There's only one way to draw a triangle. So they have to be the same if I can show that two of the sides and an included angle are congruent. Right? Head on over to the next page of the notes. We'll take a look at a few example problems together. I'll show you how this theorem works, and we'll do them together. I'll meet you guys over there on the next page.